Hello everyone, welcome to my video. In this video, we will look at a special point in rotational analysis, the instantaneous center of zero velocity. In section 5.4, when we were doing relative velocity, I mentioned it is often that we choose a convenient point where we can get its velocity or acceleration easily. Then we use that point to find out everything else. In this section, the special point we're going to look at has a very unique feature, zero velocity. Literally, zero velocity. Let's start with a tire here, a nice circle, perfectly symmetrical. We can instantly and intuitively realize when the tire is spinning, not rolling on the surface, the center of the tire has zero velocity. Note I am saying the velocity is zero, not the angular velocity, just the velocity. On this spinning tire, based on our knowledge of the geometry and physics, we know that any point on the edge will have its tangential velocity perpendicular to the radius connecting that point, where we can get the velocity such as VA is r omega. This is the point we're interested in, and we call it the instantaneous center of zero velocity. Let's look at this tire from a tilted angle here. If we construct an axis going through the center point, then we can call this axis the instantaneous axis of zero velocity. Okay, it's the same concept. On a symmetrical object like the wheel, it is probably easier to identify the center has a zero velocity. What about non-symmetrical objects like the rock? So we'll take a look at here. The rock is flying with some rotation. A and B, a random 2 point, are having different flying paths. What happened in our wheel example is the center can be connected to the edges with perpendicular lines, right? If you recall. Here we can do the same thing, but we do this reversely. For A and B's velocity, which is tangential to their flying path, we draw two perpendicular lines and extend them until they intersect at point C. Same as the point O in the previous example, point C here is actually our instantaneous center of zero velocity, because A and B are both rotating about it, and C itself does not have any velocity except for spinning caused by the angular velocity at a particular moment. Right? Similarly, to the wheel example, VA, VB perpendicular to the line connecting to C. Now we can be more generic about where to find the instantaneous center of zero velocity on any object. We can pick any 2 points on the object and connecting the line that is perpendicular to the tangential velocity of 2 points, and the intersect formed is the instantaneous center of zero velocity. We know for the same object, the angular velocity omega is the same everywhere. From A and B's perspective, it is as if A and B are rotating with the fixed point C at that particular moment. Therefore, we can write omega equals to VB over RBC also equals to VA over RAC. Then we get this relationship between A and B through the center of zero velocity. This relationship can become very handy from time to time as we solve different problems if the instantaneous center of zero velocity can be identified easily in the question. Based on what we just talked about, there are generally 3 different cases you can encounter. For 2 non-parallel velocities, this is the same as we did just now. For 2 parallel velocities, you can see from the illustration by how to draw the auxiliary lines to find the instantaneous center of zero velocity. As you can see, the instantaneous center of zero velocity can be either on the object body or off the object body, depending on the shape. Until this point, if you have been going along with the progress we made in lectures, you should realize that there are many questions we encountered before can actually be solved using the instantaneous center of zero velocity concept, which sometimes this method might be easier for calculation. Please read these two recommended sample problems. Thanks for watching. I'll see you next time.